Hi, so today we're going to look at chapter 26.2, which is the photoelectric effect. And this is basically gave experimental evidence to conclusively prove the particulate nature of photons, which I'm going to explain now. As you remember from my last video, we said photons, which are packets of energy, are not a continuous wave as we used to think they were, but instead small individual packets that have a very high frequency that only appear as if they were a wave and exhibit wave-like features. Okay, so what is the photoelectric effect? I think I should probably explain that first. So a photoelectric effect is the idea that photons can interact with electrons and atoms and actually eject electrons from atoms. So basically this occurs with metals. So what this is an experimental setup here. Say you have a metal like that, and then we have a gold leaf electroscope. And if you don't know what a gold leaf electroscope is, basically all it does is it measures a charge of something, or it measures a charge change. So basically there's a conducting rod here and a gold leaf on top of this, and initially everything is given a negative charge. So I'm going to draw that on now. Everything is given a negative charge. A gold leaf electroscope is basically a very sensitive piece of equipment which can detect changes in charge. Basically, there's this gold leaf here which is very, very light, and it's connected to a conducting band, but there's an insulating layer between them. So charge can't flow between them. And you make them both negatively charged, and what happens is when this rod is negatively charged, it causes an electric repulsion between these, and that can be easily seen. Anyway, what someone did one day is they took UV light, say a light bulb here, and they shone UV light on a bit of zinc. And what that did was it actually decreased the charge here. So suddenly, this thing started getting less negatively charged. These charges started disappearing. And you can see that because the electroscope would fall. It would fall into a lower position, meaning that it had just lost some of its charge. The electric charge on this had decreased, and this gave the idea that electrons were actually being fired off from the zinc and being lost. So anyway, how is this really relevant to this wave particle duality nature? Well, the really important thing is how the experimental results kind of worked out in the end. So they did lots of experiments, and they basically looked at how two independent variables affected the dependent variables. So I'm just going to make a list of what the independent variables were. So over here, what they tested, independent variables, were two things. They tested how the frequency or energy of the light they used affected it, and they also tested the intensity of the light. So basically, frequency, as we know before, we saw the equation E equals HF. That's right here. And we know that higher frequencies relate to higher energy levels. So that's all it is. Using protons of a higher frequency means each proton itself has a higher energy. And if you think about intensity is just a number of photons per unit area hitting a unit area. So if we're looking at the same unit area, we can say intensity is the number of protons hitting at, like, say every second, the number of photons hitting a surface. So if we are thinking of light as a wave, these two should have the same effect. Frequency and intensity both do the effect of increasing the amount of energy hitting the surface. That's no doubt about it. But the difference between the wave and the particle nature is in wave nature, both these have the same effect. In particle nature, increasing the frequency gives each individual photon more energy, thereby increasing the total energy. But increasing the intensity just makes more photons, also increasing the energy. But you can see the subtle difference there. It's like having raindrops fall on you at higher speeds versus having many more slower raindrops fall on you. They probably have the same amount of kinetic energy applied on you, but it sure does feel different. And it actually exhibits different effects right here. So what they measured, the dependent variable here, was they measured dependent variables, which is the things they measured and saw if these things had any effect. They measured two things. I believe they measured the kinetic energy of leaving electrons and they also measured the rate of electrons leaving. So that's how many electrons are leaving per second, basically. So if we are to consider this as like a wave, what do we suspect? We said if it is a wave, this is what should happen. The intensity of a radiation should be proportional to the resultant kinetic energy, and that makes a lot of sense, doesn't it? Basically, once you give it energy, the more energy you give it, the faster things should fly off. That's really logical. The second one is the photoelectric effect should occur at all intensity with all lights, regardless of intensity or frequency. And that's basically this idea here. If you say pretend you have an atom here, and this is how they probably originally viewed it. They probably saw an atom here and having its electron orbiting it, and then they probably saw light as a wave coming in, and it's basically giving this electron more and more energy, and this electron kind of vibrates more and more and more, until eventually the wave is given it enough energy that it can just suddenly have enough energy to jump off. And that's probably how they first envisioned it. So you can see how number 2 would make a lot of sense, that it should occur with all frequencies of light. It just probably take longer with lower frequencies. And finally, the last point is there should be a delay on the order of seconds with regard to the radiation's contact to the metal and the initial release of photoelectrons. And that's basically the idea that, you know, first when you start hitting the surface of this plate, all the energy is being spread out over all the atoms, and it takes a while for the first atoms to get enough energy to start jumping off. So that's, you know, that idea there. But then when they did the experiment, they found out that all of these observations were completely, totally wrong. This is what the experiment showed, which is completely contradictory to what we thought it would happen. Firstly, the intensity. The intensity of the light source had no effect on the max kinetic energy. So this was really weird. The more photons we shot at it, the speed at which the electrons left was the same. Below a certain frequency, the photoelectric effect does not occur at all. So once your frequency is below a certain point, the electrons suddenly stop leaving. And what they found was this is a really sharp cutoff point. You might have a really nice steady flow of electrons. You decrease the frequency by say 10 Hertz, and then all the electrons emission gets cut off completely. And that was very bizarre as well. And the last one is there is no significant delay, less than 10 to the power of -9 seconds between activation and emission. And this is really strange as well. This is saying that the moment light hits the surface, electrons immediately become emitted, which doesn't make sense if light is a continuous source of energy. So all three of these experimental observations didn't support the idea that light was a wave. And then what was really nice is that Einstein's theory that light wasn't really a wave, that light was actually particles, like we talked about in our last video, supported this greatly, and I'm going to show you why. So you have to remember, this is what they thought would happen, and this is what would happen theoretically with a theoretical wave behavior. This is how a wave would behave, and this is what actually happened. And you'll see in a second why this is really significant and how this kind of proves it. So basically what they found was how this works is this is how Einstein theorized it works with its particle nature. Basically, a single photon will come and hit an atom, and that one photon will give all its energy to one electron, and that one electron would suddenly it would do one of two things. Either, if it had enough energy, it would just start immediately jump off, or if it didn't have enough energy, it would get excited and instantaneously release its excitement. Because remember what we know, electrons don't like to have energy. Things in the universe like to be at a low energy state. So if you suddenly shove a whole bunch of energy on them, they're not going to be too happy about that. And so they get the energy from one photon and then they release it straight away. And you can have a stream of photons hitting it. If you like, you can have a whole train of photons, but if it releases the energy after each one, then if all of these, remember, all of these photons have the same energy, because of a certain frequency, all of the photons have the same energy. And if none of them have energy to release it, what will happen is this one gets absorbed, and then it'll drop down and release energy. The next one absorbed, drop down, release energy. And this shows the photons aren't a continuous wave of energy. It's not a continuous stream of energy. It's packets of energy, in fact. And that's a really, really interesting thing. So what happens is the energy comes along and it hits it and then emits some energy. But then what about the excess energy? I mean, the electron always needs some energy to escape. But what about the extra energy of the photon? Because the photon will give probably a little bit more, either not enough or a little bit more energy. The extra energy is measured as kinetic energy of electrons. And this is the other thing. Here, the intensity of light source has no effect on the max kinetic energy. And remember what we said, one photon can only affect one electron. So then logically, as it follows, that if we give it more photons, it's not going to do anything for the energy of these electrons, because only 1-to-1 ratio. So when we, basically, the only way to make electrons go up faster is to give each individual photon more energy. So frequency up will mean an increase in the kinetic energy. But in the same way, if you look at it from the other way around, having a higher frequency of photons doesn't mean that more electrons are going to be emitted. If a photon has enough energy to shake off an electron, fine, that's it. Giving it more frequency does not give it a higher emission rate. And let's call emission rate current, because that's what it really is, right? It's for current. So, alright, current. But what about intensity? So we already discussed why having a greater intensity doesn't mean any electrons would have more energy, because it's a one-to-one relationship. They're monogamous, if you want to think of them like that. But if you think about it, if we have more photons, obviously that means that more electrons are going to be excited. So having a higher intensity, I've just gone and dug myself a hole now. Intensity equals higher current, which I had to kind of fix up because they're both I. But then having a higher intensity has no effect on the kinetic energy of the particles. And this is also explaining this no significant delay. It's not a stream of energy exciting the electron, it's an instantaneous burst of one photon entering and leaving. And this also explains the second observation. Below a certain frequency, the photoelectric effect does not occur at all. So if these photons have just not enough energy to excite this, it's not like the first one can come in and the second one can help it. It's a one-to-one relationship. The energy goes in and it either releases or gets released. And then the next one can come in and it will do exactly the same thing as the first one. So that's why below a certain frequency the photoelectric effect does not occur at all. So you can see how frequency and intensity relate to the kinetic energy and rate of emissions of electrons now. And you can kind of see why the particle nature really well explains these experimental observations of how the photoelectric effect works. And this kind of covers point C. Show our understanding that a photoelectric effect provides evidence for the particulate nature of radiation. While phenomenon such as interference, well then we have ideas such as light can interfere and have diffraction patterns that can provide for wave nature. So then we kind of give an idea of both, but we'll discuss them in the next video. But this is the idea of you know. This one here. This stuff here. How the intensity and frequency affect the kinetic energy and the current, and the experimental observations here. And this is really what you need to know for that. These 3 points. Below a certain kinetic frequency, photoelectric effect does not occur at all. Intensity does not affect kinetic energy, and there's no significant delay. And you can also, make up some more ones, like saying having a higher frequency does not affect the rate of emission, whereas in this one it would, because in this one it's all about total energy. So this kind of made us rethink light. Light isn't just about the total energy; it's about packets of energy hitting an electron. And now we have to explain the significance of a threshold frequency. So to do this, I'm going to go ahead and draw a bit of a graph. So, actually I'm out of time in this video, so I'll see you over in part 2.